Let's explore principal component analysis or PCA. We'll see what is PCA, the core intuition behind PCA, why we need PCA, and then high-level mathematical foundation of PCA. We'll also deep dive and see why covariance matrix, eigenvector and eigenvalues are used in PCA. This math part I have tried to make as simple as possible for understanding. Now, how PCA works, we'll see a step-by-step process. How do we calculate? Then advantages and limitations of PCA, when to use, when not to use PCA, and lastly, PCA in practice or few applications of PCA. Now, what is PCA? It's an unsupervised technique for dimensionality reduction. So, if you have these features in our training data for a house like living area in square feet, number of rooms, number of bathrooms, lot size, garage size, basement size, neighborhood score, distance to city center. Now, there are lots of features in this data set, and if you see living area, number of rooms, number of bathrooms, lot size, garage size, basement size, all this kind of related. This talks about the overall house size and quality. If you see this neighborhood score and distance to city center, it kind of talks about the location of the house. So instead of having these 8 correlated features, we can have 1 or 2 meaningful features. So that's when we'll apply PCA or principal component analysis. So after PCA, we can have 1 or 2 principal components. So first principal component, it can be about overall house size and quality. We'll have living area, number of rooms, lot size, garage size, etc. In PC2, the principal component 2, it can consider the location perspective like distance to city center, neighborhood score, etc. So instead of 8 correlated features, we model 2 meaningful dimensions or features. Next is the core intuition behind PCA. So here we have few 2-dimensional points. I have taken 2 dimension because of simplicity. So we have x-axis and y-axis. So this x-axis is for feature 1, this axis is for feature 2. So how do we find the coordinate of any data point? Let's say this point. We'll project the point onto this axis. Then we'll get this length or this length. This is the x length. And if we project the data point onto this axis, you will get this y length. So what we do in case of PCA is we rotate the axis. So in place of this axis and this axis, let's say we have rotated the axis. This rotated axis will be calling principal components. So this is, let's say we have taken 2 principal component in this picture. This is principal component 1. This is the direction of it, and this is principal component 2. This is the direction of principal component 2. So for any data point, then we'll project onto this principal components, and then we'll get this length. If you project this point onto this principal component, we'll get this length. So that's how we will rotate the axis in some way and we'll project the data point onto that line. So how do we reduce the dimension here? So in this case, we have shown 2 principal components, right? But anyway, we are talking about 2-dimensional data, and from 2 dimension, we want to go to 1 dimension. That's the only possibility we have for 2-dimensional scenario, right? So we'll just take 1 principal component in this case. So we had a 2-dimensional data earlier here, and we'll just rotate the axis in such a way that axis will be enough to display this data. So we'll just take 1 principal component to convert from 2D to 1D. So if we have 3-dimensional or multi-dimensional data, we can decide we can have 1 or 2 principal components. So we can take multiple axes in that case. So the core intuition of PCA is it finds new axes or principal components. Principal components are orthogonal to each other. So all the axes will always be orthogonal to each other. This axis capture maximum variance of the data. So if you see this axis, if we choose, this axis will be capturing the variance of the data nicely. So that's why we are rotating in this direction. So projects data onto fewer dimensions. So from 2D, we'll just take one PC, we'll project the data on that principal component direction. Now, why do we need PCA? It's difficult to work with more features or more dimensions in our ML models. So the accuracy of ML models also gets impacted by more dimensions. The more the dimension, the lesser the accuracy of prediction. Few other problems is like redundant features and high computation cost. So if we have redundant features which is not adding any extra benefit for the model, we'll just increase the computation cost, right? And also it will add noise and overfitting to the training. Visualization difficulty. So beyond 2-3 dimension, it's difficult to visualize. So of course PCA helps in visualization. Now PCA helps simplifying the data while preserving important information. So data variance capture is maximized in PCA and dimensions are uncorrelated in PCA. Now it's kind of like taking photos. Like if you have multiple people standing, you can take photo of the people from different angle, right? But which angle is better? So if you take photo from this angle, there will be lots of overlap, right? You might not cover all the people nicely. If you take from this angle, you might not cover all the people, right? You can cover only just a portion of the people. If you take photo from this angle, then you see this looks like a better approach. Your photo will look like this, like you can cover all the persons nicely. So it's the principal component analysis is like taking a photo of the data. So if you're taking a photo from this angle, your photo will be like this. You will be able to capture all the points in this photo. Now, how to capture the maximum possible variance in the data, right? So if you see, if you take photo from this angle, so this captures most variance of the or spread of the data. So this angle looks better. Now we can capture data multiple times from multiple angles. That's what we said earlier, right? We can have multiple principal components. One capture means one principal components. If you capture from this angle, you will get a photo like this, right? If you capture from this angle, you will get a photo like this. If you take from this angle, you might get a photo like this, right? So from which angle to take the photo of the data? So from which angle to capture? That's the main point. Now how to convert 2D to 1D? So we just have to capture one time only. So that's already we have discussed. So we have to capture one time from best angle. So this looks like the best angle. So let's say you have taken this rotated axis. So you are taking photo from this angle. You are getting a photo like this. And this is the rotated axis in your case, right? So all the data points will be projecting onto this rotated axis. So this will be your principal component and these points are the projected points. Also, if you take this principal components in this direction, then you will be projecting the points onto this vector, this axis, right? And this will be the projected points. Now, which projection is better? So, in this case, you get a projection like this. In this case, you get a projection like this, right? Here in this case, you see the space between the projections are very clear. And here there is lots of overlap. So, of course, definitely this projection is far better. Now the main problem is how do we find the projection, or before that how do we find the principal component or the new rotated axis. So if you find the new rotated axis or the principal component, then we'll be projecting the data onto that new axis. So next we'll discuss about the mathematical foundation, high level mathematical foundation. How do we find the projection and how do we find the principal component? So PCA is based on covariance matrix, eigenvalues and eigenvectors. So there's three main concepts. So you don't need heavy math to understand PCA conceptually. I will try to make it as simple as possible. So we just need to find the principal component. So let's call it W, and these are the points, right? Let's say this is one point X, this can be another point X1 and so on. So we need to find the W. This is the direction of the new axis, new rotated axis or principal components. Now first try to understand the projection. So there are two concepts. One is the scalar projection and one is the vector projection. So before going there, let's see the normal projection in X and Y axis. So let's say if we have few points like this. For any points, you project the point onto X axis, you get this length. You project the point onto Y axis, you get this length. This lengths matter, right? So that's how you get the coordinates of the point. So now we are talking about the rotated axis W, scalar projection of X onto W. Now what is the scalar projection? Scalar projection is the length or the magnitude of the shadow of one vector onto another. So this W is the vector, target vector we want to find out, and X is the data point we have. So you want to find out the shadow of X onto W. So let's say light is coming from above. So what will be the shadow of X onto W? This length. So basically we are projecting then this X onto W, and this length we want to find out. That is the scalar projection. So it's a single real number, a scalar value. And let's consider this, the angle between X and W is theta. So this length will be norm X cos theta. But how do we find this norm X cos theta? So there is this formula that we know already. So dot product of X and W is norm X times norm W times cos theta. What do we want to find out? Norm X cos theta. So norm X cos theta is X dot W divided by norm of W. So that will be the scalar projection of X onto W. X dot W divided by norm of W. X dot W is W transpose X divided by norm of W. The scalar projection is a real number and it can be positive or negative depending on the angle between the vectors, right? So this angle will decide whether the scalar projection is positive or negative. So this is basically the length of the desired projection. Next comes vector projection. So in scalar projections we found out this length, but we don't know the direction of W. We want to find out W, right? So W will have one length and direction. So the vector projection of X onto W is an actual vector that points in the same direction as the target vector or the opposite direction if the scalar projection is negative, and its magnitude is the scalar projection. So the vector projection of X onto W is one vector that is pointing in this W direction, and its magnitude will be the scalar projection. So this vector basically. So vector projection of X onto W will be this multiplied by this. What is this? X dot W divided by norm of W. This is the scalar projection. And W divided by norm of W, this is the direction of desired projection. So W is the vector and norm, if we divide it by norm of W, you get the direction of the desired vector W. So we are multiplying this direction of desired projection with the scalar value. So what is this? X dot W is W transpose X divided by, if you multiply this two, you get squared norm of W times this W. So this is the vector projection of X onto W. Now if we get vector W with norm 1, then norm of W is 1. So vector projection of X onto W will be W transpose X times W from here. This part is 1. So that's because we want to find out W, we are assuming norm of W is 1. Then we get a simplified equation of vector projection. So for our problems, we have these points, right? For each x, we'll get an approximate x hat projected onto W. So for each data point, we'll project the data onto this W. This is basically the W, and we get the projected points here. So this projected point will be the vector projection, right? So that will be W transpose x times W. Considering we have found the vector W with norm 1. So this is the vector projection of x onto W. Now to find the best direction of W, like we have to minimize the error between x and this x hat. So squared norm of x minus x hat, this should be small, minimized. If we expand this, what is x hat? X hat is W transpose x times W. This should be minimized. Let's expand this. This we get x transpose x minus 2 times W transpose x times W transpose x plus the square of this whole thing, W transpose x whole square times W transpose W. We get x transpose x minus 2 times W transpose x whole square plus W transpose x whole square, because W transpose W is squared norm of W, which is also 1, as we have assumed already. So we get x transpose x minus W transpose x whole square. So this should be minimized for any small point, for any point x. Now we have multiple points. So instead of one point, consider the random vector x. So all the points are coming from this capital X. We need to minimize the expectation in that case. So we'll just replace the same derivations we have here with capital X. So we have to minimize expected value of x minus W transpose x times W whole square, and we get, using the similar derivation from previous slide, we get E of x transpose x minus W transpose x whole square from here. We can write it as E of x transpose x minus E of W transpose x whole square. This thing should be minimized. If this to be minimized, consider a few things. Our unknown vector is W that we want to find out, right? But this part, you see, E of x transpose x, it doesn't depend on W. We can just ignore this part. Then we have to minimize this minus of this part. But this E of W transpose x whole square, this is positive. This is a squared value, this is a positive one. So that means we have to maximize E of W transpose x whole square. This thing we have to maximize. So we will be maximize this expected value of W transpose x whole square. Now let's expand this. W transpose x whole square, if we expand this, we get W transpose x, x transpose W. Expected value of that. We can keep this W outside, so we get W transpose E of x transpose W. So consider this E of x transpose is C, so we get W transpose CW. That is something we have to maximize. So our objective is maximizing W transpose CW, where norm of W is 1 and C is E of x transpose. Now what is this C? We have to maximize W transpose CW, right? So what is this C? W we will be finding, but C is something we have to find out what is C. So consider you know about mean and variance of x. Mean is at center, so we get Ex equals to 0, right? So what is the variance of x? E of x minus Ex, x minus Ex transpose. that is E of x minus 0, x minus 0 transpose. So we get E of xx transpose. So that is basically this E of xxt, this is basically the covariance matrix. And we have to maximize W transpose CW, where C is the covariance matrix. What is covariance matrix? It measures how features vary together. So high covariance means redundancy. Now let's pause for a moment. So we have to maximize this W transpose CW, where C is the covariance matrix. That's, we are clear till this point. Next we have to see how do we maximize this. We don't have to do a lot here. There is one thing, there is one inequality, Cauchy-Schwarz inequality. So what it says is U transpose V is less than equals to norm U times norm V. So if you just write this W transpose CW as U transpose V, where W is U, CW is V. So this is U, W is U, CW is V. So that means W transpose CW is U transpose V. We can write it as like that. Now we have this inequality where it says U transpose V is always less than equals to norm U times norm V. So for in our case, W transpose CW will always be less than equals to norm of W times norm of CW. Now max value of U transpose V is when this two will be equal, because U transpose V is always less than equals to this thing. So when this two will be equal, that will be the maximum value of U transpose V, right? So max value of U transpose V is when U transpose V equals to norm U times norm V. And when that happens, this is also comes from this principle, that is, this happens when one vector is a scalar multiple of another. V equals to lambda U for some scalar lambda. So V here in our case is CW equals to lambda U. U is W, right? So when this happens, then this will be maximized. So max value of W transpose CW is when CW equals to lambda W. Now what this equations reminds of? This is a very known equation. If you have read about linear algebra, so we'll know this. But even if you don't know, I will just quickly tell. So max value of W transpose CW is when CW equals to lambda W, where C is the matrix, C is the covariance matrix, right? So C is a matrix, W is a vector, lambda is a scalar, W is a vector. What this equation reminds of? Yes, this is the eigenvalues and eigenvectors equation. So here lambda is eigenvalue of covariance matrix C. So our objective is here maximizing W transpose CW, where C is the covariance matrix, and we saw that it happens when CW equals to lambda W for some scalar lambda. So what is the maximum value of W transpose CW? That is W transpose CW is U transpose V, let's say. That is, it will be norm of U times norm of V. Here U is W, V is CW. So max value of W transpose CW is norm of W times norm of CW. And that happens when CW equals to lambda W. So first see what is the maximum value. So it is norm of W is 1 and CW is lambda W in this case, right? So norm of CW is norm of lambda W. So 1 times norm of lambda W. But lambda is a scalar, we can get it out. So you get lambda times norm of W or lambda. So W transpose CW is lambda, that is the maximum value. of W transpose CW. So max value of W transpose CW is eigenvalue of C. Lambda is the eigenvalue and W will be the corresponding eigenvector. So now this C covariance matrix, it will have multiple eigenvalues and eigenvectors usually, right? So we need to pick large eigenvalues and corresponding eigenvectors of covariance matrix C to maximize W transpose CW. Because the maximum value of W transpose CW is lambda, the eigenvalue, right? So you always have to pick the large eigenvalues. So the covariance matrix is symmetric and positive semi-definite matrix. So the eigenvectors will be orthogonal to each other and will always have positive or non-zero eigenvalues. So if C is a D cross D matrix, it has D eigenvalues. So let's say these are the eigenvalues lambda 1, lambda 2 till lambda D, and these are the eigenvectors E1, E2 till AD. So we will pick large eigenvalues which will cover most variance of the data. So if you sort the eigenvalues, let's say lambda 1 is the largest, lambda 2 is the second largest, and so on, like lambda D is the smallest eigenvalues. We'll just pick from the largest eigenvalues. So if we want one principal component, we'll just take lambda 1 and E1. E1, this eigenvector, corresponding eigenvector will be the principal component or W. If we want two principal components, then we'll consider the next W as well. Now, covariance matrix is symmetric, so eigenvectors will be orthogonal to each other, right? So eigenvectors are orthogonal to each other. That means the principal components are orthogonal to each other. So these eigenvectors are the principal components that will be orthogonal to each other. So earlier also we talked, because we are rotating the axis, we are getting new axis. So here this also satisfies here because principal components are orthogonal to each other. Axes always will be orthogonal to each other. Lastly, see how PCA works. So if we are given few data, how do we compute the principal components? How do we compute the projections of the data on the principal components? First, we'll standardize the data. Then we'll compute the covariance matrix. We'll compute eigenvectors and eigenvalues of this covariance matrix. Then we'll sort the eigenvectors by eigenvalues. The eigenvectors will be the principal components. We'll sort the eigenvectors by eigenvalues and we'll pick the top k or largest k components. Then we'll project the data onto this new space or new principal components. That's how we'll do this PCA. So here this covariance matrix we already talked, it measures how features vary together. Eigenvectors are any eigenvalues. So eigenvectors is basically the directions of the principal components, the W's, and eigenvalues, it defines amount of variance captured. So if you see the equation we had, W transpose CW equals to lambda, right? So lambda is the eigenvalue, that is W transpose CW, and our aim was to maximize this W transpose CW. And what actually we are maximizing? We are maximizing amount of variance captured. So that is eigenvalue here. Next, see a few advantages of PCA. It reduces dimensionality. It removes the noise from the data. It speeds up training, reduces overfitting, helps in visualization, of course. Few limitations of PCA: loses interpretability. So let's say if we have a 8 or 10 dimensional data and we are just converting it into a 2-dimensional data, right? So we don't know what these dimensions actually mean. So it loses interpretability in some cases. It's linear only. It's sensitive to scaling. We need to scale the data properly. Then we can apply principal component analysis. It's not ideal for non-linear data, of course. Now, when to use PCA and when not to use PCA? We use PCA when we have high dimensional data, the features are correlated, we need to visualize the data, and we are doing the pre-processing step to convert from higher dimensions to lower dimensions. When not to use PCA? When interpretability is crucial, when data is non-linear, then we cannot use principal component analysis. Finally, there are multiple practices of PCA. It's used in image compression, face recognition, noise reduction, feature processing, and various exploratory data analysis.